The next calculation that I wanted us to look at is how energy is related to frequency, and that is shown in the equation below, which tells us that the energy of a photon, which is a unit of light, is equal to a constant. You see that value here. This value for this h will not change, so that will always be known, similar to the value for c that we saw in the previous equation. And then we have frequency multiplied by that constant, and that will give us the energy. What we can see from this equation is that with our constant being here, multiplied by the frequency, if the frequency goes up, and this is a constant, it's not changing, then the energy has to go up. And similarly, if the frequency goes down, and it's being multiplied by a constant value, then the energy must also go down. So the energy and the frequency must be what we call directly proportional. One goes up, the other one goes up. Now recall from our last lesson that we learned the speed of light is equal to the wavelength times the frequency. So we saw there that the constant c is over here. So wavelength times frequency have to equal a constant value. So if the wavelength goes up, and it has to multiply to make something constant, then the frequency has to go down, and vice versa. If the frequency goes down, the wavelength goes up. Excuse me, I said that backwards. If the wavelength goes down, the frequency goes up. Wavelength goes up, frequency goes down. These are what we call inversely proportional. Right? But you will see here that they both have this v, or frequency, in their equations. So therefore, we can combine these two ideas. We can relate wavelength to energy, and energy to wavelength by way of the frequency. All right, and so that's what they're going to ask us to do in these example problems. So we have an example where sodium, the metal, is excited and emits a yellow light, and that wavelength of light is 589 nanometers. Now, if we've done the flame test lab already, then we saw an example of this, and if not, then we will. Okay, but certain metals, when they're heated, their electrons are going to move to a higher level, and then when they fall back down, they're going to give off light. And in the case of sodium, it emits a light with a wavelength of 589 nanometers. We want to find the energy of this light. All right, so we have the wavelength, and we're looking for the energy. Okay, so the wavelength equals 589 nanometers, and we're looking for the energy. So let's start with speed of light equals wavelength times frequency, and we can use that to find the frequency, and then we can say energy equals Planck's constant times frequency. Right? So we'll start here by finding the frequency. So we're going to divide both sides by wavelength. So the speed of light divided by the wavelength equals the frequency. And remember, speed of light is a constant, 3.0 times 10 to the 8th meters per second. So speed of light. And the wavelength they gave us was 589 nanometers. But our wavelength has to be in meters to match the speed of light. So remember to go to meters. We just multiply by 10 to the negative 9th. So now that's in meters. Right? And when we do that math, that's going to give us our frequency. Okay, so recall on our calculator how to use scientific notation. 3.0, and then we do EE for the exponent, 8 divided by 589, exponent, negative 9. And my calculator says that that is 5 point, I want to keep 3 digits, 5.09, that's 3 digits, times 10 to the 14th, 1/2 is the unit, because these meters can cancel. All right, so that is my V, and I'm going to plug that in to my energy equation. So energy equals Planck's constant, which is 6.63, times 10 to the negative 34 joules times seconds. You do not have to memorize these constants. So the value for H and the value for C, you can always look up those numbers. All right? So here we're calculating energy, which is Planck's constant, which will always give you that, or you can look it up, times the frequency, which we just calculated, 5.09 times 10 to the 14th, 1 over second. So notice my seconds will cancel, so I'm going to be left with joules. Put this in my calculator. 6.63 exponent negative 34 times 5.09 exponent 14. That will be 3.37, that's 3 digits, times 10 to the negative 19 joules. Right, that is the energy for one of those photons that's coming off of the sodium atom. Right, they work this problem out in a slightly different way, which I wanted to show you. So they start out, we're looking for energy, and then they look at the equation for frequency, which we rearranged when we were working the problem. We said frequency equals speed of light over wavelength, and they just go ahead and plug that in for frequency. So they have that right here, which we solved for, and then they multiply it by Planck's constant. Their seconds and their meters cancel, so they're left with joules, and it's this same answer we got, except for this last digit. We got a 7, okay, and those are just rounding differences. So this is the amount of energy that is in each photon that comes off of that sodium light. All right? So go back and review how to do these calculations, how to do wavelength and frequency, as well as energy calculations, and you'll have some of those to do on a worksheet.